Let's start solving the question number 90. Okay, read each statement. It is given to find the correct statement. Okay, so option A is given that for Fermi selection rule, beta decay in beta decay del J equal to 0, and there is a parent change of del P not equal to 0. Okay, and is allowed transition. And option B, del J is equal to plus minus 1 0 and parity change is equal to 0 is first forbidden in gamma modular selection rule. And in option C, there is a reaction in which a helium is converting into a lithium with the help of a beta negative decay. Okay, and in option D, oxygen is converting into nitrogen with the help of a beta positive decay. Okay, and the main thing is here in the option D, this nitrogen is in fast accelerated state. Okay, and what is the statement are given in option C? In this decay, uh, lithium is not governed by pure, this reaction is not governed by pure gamma molecular transition, and in option C it is given that the transition is governed by pure Fermi selection rule. Okay, so we have to find the correct statement. Okay, now you see in nuclear physics, whenever we talk about J, J is denoted as spin. What is the spin? It is not a spin as we have studied in atomic and molecular physics. Okay, in atomic and molecular physics, we have studied that spin means S. It is denoted as S. Okay, but here in nuclear physics, spin means J, or we can say capital I, capital J or capital I. Okay, so in nuclear physics, J means spin. That is the total spin. That is the total angular momentum of the nucleus. Okay, it is a combination of, as you know, spin angular momentum and orbital angular momentum, S plus J. Okay, it is a vectorial combination of S and J. Okay, so on the basis of this argument, let's start. We have to first know what are the transition rule for a beta decay, and we have to you should keep in mind that one thing, that is here we are taking only two cases, that is beta negative and beta negative, and we are skipping the other types of beta decay, which is electron capture. Okay, here this type of reaction is not mentioned in these four options, so we have to restrict our argument between beta negative and beta positive decay. Okay, so let's see some basic knowledge to solve these four options. Okay, to find the correct option. Okay, we have to find the we have to see the what is the basic statements beside the behind the transition rule in beta decay. So let's see. Okay, this is the 19 number question, and in this question, to give you a idea and to give you a basic information, we have given that X is the parent nucleus. Okay, and Y is the daughter nucleus, and this E means it can be electron or it can be positron. Okay, and a nu means it can be neutron or it can be anti-neutron. Okay, so as you know that in beta decay, after the formation of the daughter nucleus, if the beta decay is beta negative decay, then what happens that a neutron is converted into a proton. So if a neutron is converted into a proton, then there is a formation of a, or we can say there is a formation of outgoing particles of electron and anti-neutrino. And if the reaction is not beta negative decay, and let's suppose it is beta positive decay, then the outgoing particle is a positron and a neutrino. Okay, so for a basic example, I have taken X as a parent nucleus and Y is the daughter nucleus, and E and nu are the a kind of outgoing particle. Okay, so as I mentioned that it can be electron, positron, neutron, anti-neutrino, like this. Okay, so this Jp is the spin of the parent nucleus, Jd is the spin of a daughter nucleus, and J vector E bracketed E and nu means in the spin of this outgoing particle, net spin of this outgoing particle. Okay, so if a reaction after the, let's suppose this is the parent nucleus and it is in the origin initially, so after the formation of this outgoing particle, so this outgoing particle, let's suppose this electron is moves in this direction, and this anti-neutrino is moved in this direction. Okay, this antineutron moves in this direction. Okay, so what happens that generally what we see that in the reaction, in the nature, what happens that the parent nucleus and the daughter nucleus remains at the origin. Okay, that means let's suppose it was initially at rest. That means after the formation of after the reaction of beta decay or beta positive decay or beta negative decay, the parent nucleus, whatever position it was accorded before, after the reaction the daughter nucleus is also at the same position. Okay, and the outgoing particles here is electron, positron, neutron, antineutron, whatever. Okay, so these are outgoing particles. Okay, what happens is that these outgoing particles will take zero momentum from this reaction. Okay, it is it is seen in the many reactions. Okay, naturally happening reactions. Okay, so as these these electrons and or we can say these outgoing particles are taking any momentum, any angular momentum, that means the net angular momentum of this outgoing particle is equal to 0. Okay, so why they are taking 0 angular momentum? Because we are considering that the outgoing particles are forming at the center of this parent nucleus. Okay, so as they are forming in the center of the parent nucleus, that means the angular momentum, as you know, L equal to R cross P. Okay, so as they are, we are considering as they are forming at the at the center, that means the R value equal to 0. Okay, let's suppose this parent nucleus has a radius of R. Okay, and the outgoing particles are forming at the surface and they are coming tangentially. Okay, then what happens? Then there is a angular momentum for the outgoing particle, because R equal to the angular momentum equal to R plus P. So if this electron or neutron is moves or come out from the parent nucleus in this direction, then there is a angular momentum because L equal to R plus P. But if these outgoing particles are coming or are formed at the center of this parent nucleus, then what happens? The R value becomes 0. Okay, because they are forming at the center. So at the center R equal to 0. So that's why L equal to 0 for both particles. That means electron and a antineutrino or positron and a neutrino. So that's why the combined angular momentum for the outgoing particle is equal to taken as a 0. Okay, so hope you are getting what I am specifying or trying to understand you. Okay, so L equal to 0, and this is the most probable thing, and we are not assuming it. Okay, this is the naturally happening things, and we have to take. That's why we took that L equal to 0 for the outgoing particle angular momentum value. Okay, orbital angular momentum value. So if the orbital angular momentum value for the outgoing particle is equal to 0, then what is the J value, or we can say the spin of the outgoing particle, or we can say what is the change in the spin of the parent nucleus and the daughter nucleus. How can you find? So for that we would find the spin of the particles, outgoing particles. So the spin, we know that the spin of an outgoing particle is an intrinsic property of that particle, and this property cannot be extracted from the particles because it is intrinsic in nature. Intrinsic means it is forever present. Whenever when you put it in any space, any field, this spin is an intrinsic property and it will remain with the particle at every time in any situation. So that's why the spin, and we know that for electron and a neutrino both are half spin particles. So the net spin will be a vectorical addition from 1 by 2 plus 1 by 2 to 1 by 2 minus 1 by 2. So the net spin equal to 0 and 1. Okay, so that means the spin of a outgoing particle can be 1 and can be 0. This is the combined spin. You remember it. This is the combined spin. That means when this 1 is possible, that means spin equal to 1 is possible when it is parallel spin, when both have parallel spin, and when S equal to 0, that means it is anti-parallel spin. Both outgoing particles have an anti-parallel spin. Okay, so you see, now you see when this Fermi allowed transition is possible. Okay, you remember that when S equal to 0, that means it is Fermi. Okay, and when L equal to 0, the orbital angular momentum of the outgoing particle is 0. That means it is allowed. Allowed means it is highly possible to happen. Okay, allowed means it is highly possible to happen. Okay, and S equal to 0 means Fermi, and L equal to 0 is equal to allowed. That means for allowed Fermi transition, the rule is L equal to 0, S equal to 0. Okay, so if L equal to 0 and S equal to 0, what is the J value, the spin of the outgoing particle? We know J equal to L plus S. So you add this, 0 plus 0 equal to 0. That means what? That means the change in the spin of the parent nucleus and the daughter nucleus is in 0, because the outgoing particles are taking a spin of 0. Okay, so as I have written here, look at this equation. The parent nucleus spin, daughter nucleus spin is addition of this daughter nucleus and outgoing particles. Okay, so if this is how much? 0. Then what does it mean? If this is 0, that means what? The spin of the parent nucleus is equal to spin of the daughter nucleus. Okay, so whatever spin was present before the reaction, that much spin is present in the after the reaction. Okay, that means there is no change in spin. Okay, this is the condition of a Fermi allowed transition. Okay, see, this is the condition, del J equal to 0. So allowed Fermi transition, L equal to 0, S equal to 0, del J equal to 0. This is the allowed Fermi transition. So for now, let's find how to find the parity change. We know parity change. How can you find parity change? This statement is not correct. Okay, let it omit. You look this statement. Okay, so del P equal to del pi. We can do it, or we can find the change in parity by subtracting the initial parent parity. That means the whatever the parity was parent nucleus, and with from the reactant side, because in the reactant side there are 3 particles. One is daughter nucleus, another is electron or positrон, and the last one is neutron and antineutrino. Neutron and neutrino and antineutrino. Okay, so you see minus 1 to the power L. Okay, so why this L is present in both sides? This you see, for parent nucleus and daughter nucleus the L value is the same. Why? Because both are same, both have same angular momentum. Okay, as this L equal to 0, you see this L equal to 0, that means the outgoing particles are taking no angular momentum when they are coming out from the nucleus, parent nucleus. So if the outgoing particles are not taking any momentum from any angular momentum from the parent nucleus, that means what? That means whatever angular momentum was present before with the parent nucleus is also present after the reaction. Okay, that's why this L value is same for parent nucleus and daughter nucleus, but we don't know what is the L value. Okay, now you see, this is the reactant side parity and this is the parent side parity. In the parent side there is only the parent nucleus. Okay, so that's why this is and this is. Okay, and we know that Le plus L nu, when you add this Le plus L nu, it will be L. And what is the value of L? L equal to 0. Okay, L equal to 0. Le plus Le plus L nu is nothing but the value of L. Okay, this value. Which value? This value. Value of L. This value. Okay, this is L value. Okay, so if you put 0 plus 0, then it will be 0. So 1 to the power 0 equal to 0. So what you find? You find both terms are same. So the change in parity equal to 0. That means there is no change in parity for this reaction for Fermi allowed transition. Okay, now see what is the gamma out transition. For L equal to 0, and for S equal to 1, it is allowed gamma out transition. For S, you remember that for S equal to 0, that means it is Fermi. We don't know, let's suppose we don't know the value of L. But if it is mentioned that S equal to 0, that means it is allowed. sorry, it is Fermi. And but if it is mentioned that S equal to 1, that means it is gamma Teller transition. Okay, but we don't know, let's suppose we don't know the value of L value. Okay, so then what means that? It means that if S equal to 1, that means it is gamma Teller. It is not Fermi. It is confirmed. Okay, so you see, if S equal to 1 and L equal to 0, then what is the spin of outgoing particle? The spin equal to L plus S. That means L equal to 0 and S equal to 1. That means the spin of outgoing particle is 1. Okay. Now in this case, you see that there is a change in speed between the parent nucleus and the daughter nucleus. Why? Why there is a spin change? Because the outgoing particle is now taking a angular momentum. Sorry, a spin. Okay. Because here the S equal to 1 now. Okay. Angular momentum is 0. You see, angular orbital momentum is 0. But here, as S equal to 1, so that's why a spin has been changing. Okay, and the spin change is 1 vector. Okay, you see, that's why we put 1 vector here. The parent nucleus is this, and the daughter nucleus is this, and there is a change in spin of 1 vector. And this 1 vector can take 3 values. It may be 1, it may be 0, or it may be -1. That means what? That means there is a change of a -1. There is a change of a spin of the parent nucleus and daughter nucleus of a +1, 0, and a -1. For example, if the daughter nucleus has a spin of a 2, then what is the possible value of a spin of the parent nucleus? Okay, so as you know, L value, sorry, the spin value of outgoing particle is 1. That means, so if you put 2 vector plus 1 vector, then there is a factorial addition. In that factorial addition, if you do it, you will get a 2 plus 1 to 2 minus 1 values of the spin of the parent nucleus. So what is the possible values? What are the possible values? It may be 3, 2, or 1. So 3 value will be possible depending on this value. Depending on this value. So for allowed gamma Teller, L equal to 0, S equal to 1, and change in spin between the parent nucleus and the daughter nucleus equal to 1. This is the allowed gamma Teller transition. Okay. And what is the parity of the parity change? What is the parity change? Parity change equal to 0 because L equal to 0. Still the value of L equal to 0. You see, still we are considering L equal to 0. Allowed means L equal to 0. So whenever there is allowed, the parity change equal to 0. Always. It is confirmed. Okay. So parity change equal to 0. Acha L equal to 0. Because parity depends on -1 to the power L. Parity depends on angular momentum value. So as the angular momentum value is equal to 0. Okay. So whatever angular momentum was before, that much angular momentum was present after the reaction. So parity change equal to absolutely 0. Okay. Now you see, if let's suppose in any reaction the L value is not equal to 0, that means it is not allowed. But still the beta decay takes place. Then what we can argue in this type of reaction? We can say that this type of reactions are forbidden. Forbidden means it is not allowed. It is the dictionary meaning. Forbidden's dictionary meaning is not allowed. Okay, no, but in nuclear physics, forbidden means in this case it is allowed, but the probability of happening such type of reaction, that means L equal to has higher values, L equal to 1, 2, 3, has a lesser probability as compared to the value of L equal to 0. Okay. Hope you are getting the answer, questions of what I am talking. Okay. So for L equal to 1, this is the first forbidden. Remember that the possibility or the probability of happening of L equal to 0 reaction has a higher probability. We can say that 100 times more probable than L equal to 1 reaction happen. Okay. So and L equal to 2 is the second forbidden. L equal to 3 equal to third forbidden, like this. Okay. So if you see for L equal to 0 and L equal to 1, this is the first forbidden. What you see? First forbidden, S equal to 0, first forbidden Fermi transition. But if it was not S equal to 0, let's suppose it was S equal to 1, then what is the reaction? It is first forbidden gamma Teller. I have just said you that For s equal to 0, it is for s equal to 1, it is gamma modular. Okay, and for L equal to 1, it is fast forbidden. Fast forbidden, s equal to 0. That means fast forbidden Fermi transition. For s equal to 0, L equal to 2, fast forbidden, sorry, second forbidden Fermi transition, like this. Okay, and for, you see, and what is the parity change? Parity change equal to minus 1 to the power L. You see, depends on L value. This L equal to 1, so minus 1 to the power L equal to minus 1 to the power 1 equal to minus 1. Negative parity means there is a change in parity, because here del p or del pi equal not equal to 0, because it is you are getting minus 1, so there is a change in parity. Similarly, for s equal to 1, L equal to 1, it is fast forbidden gamma modular. S equal to 1, that means it is gamma modular, and L equal to 1, that means it is not allowed. And and L equal to 1, that means fast forbidden, not allowed. Okay, and what is the parity change? Again, it is depending on L value, and L value equal to 1. So minus 1 to the L equal to 1. So again, you are getting minus 1. That means again there is change in parity. Okay. So on this explanations, let's start doing each questions by reading each solution. Okay. Now you see option A. In the option A, it is given that for Fermi selection rule in beta decay, del J equal to 0, and there is a parity change of del P not equal to 0, and it is allowed condition. Now you see, as del J equal to 0, so it is, that means it is what? Del J equal to 0. That means it is what? It is a condition of a Fermi transition. You see, this, you see this del J equal to 0 here. This is okay. Now you see what is the second statement? Del J equal to 0. This is correct. And there is a parity change of del P not equal to 0. Del P not equal to 0. Now let's see. Del P not equal to 0. You see, here we are getting del P equal to 0. Okay. So that's why, as in the question it is mentioned that it is not equal to 0. That means the option A statement is not correct. Okay, this is not correct, because we have to find the correct statement. Okay, now you see option B. In the option B, it is given that del J equal to plus minus 1, 0, parity change equal to 0 is a fast forbidden gamma modular selection rule. Now you see, for gamma modular, what is the del J value? For gamma modular, what is del J? For gamma modular, you see this. For gamma modular, the change in del J is equal to positive 1, 0 or negative 1. See, this change, the spin of outgoing particle, that is nothing but the change in spin between the daughter nucleus and the parent nucleus. Okay, so you are getting del J equal to plus minus 1 and 0, this 3 value. Okay, now you see, so in option B, this is correct. Okay, this statement is correct. Now you see what is the parity? Parity equal to 0. Now you see what is parity? Parity change. Yes, you see del P equal to 0. You see, it is also the correct statement. This is also correct statement. This is also correct. Now it is given that is fast forbidden. This was not correct. Okay, these two statements are correct, but if these two statements are correct, it is becoming a allowed gamma modular transition, but it is given that it is fast forbidden gamma modular transition, so this is an incorrect statement. Okay, now you see option C. For option C, there are two. There is a transition. It is transiting with the help of beta negative decay, and we are given that it is not allowed by pure gamma modular transition. Now, what you have to find? To solve this kind of question, we have to first determine the spin parity of the daughter nucleus. This is the parent nucleus, this is the daughter nucleus. Okay, the spin parity of the parent nucleus and daughter nucleus. Then we have to apply the whatever kinds of cell model rule. Then you have to find the spin parity. Then you have to see what kind of transition is possible with this spin parity change. Okay, so you see first, this is the parent nucleus. This is a even types of nucleus. So its spin parity will be 0 positive, as all the neutrons and protons are paired off. So as they are paired off, that means what? The spin equal to 0 and the parity is even. Okay. Now you see, as helium is converting into lithium, and lithium has a proton number 3 and a neutron number 3, as its A number equal to 6. Okay. So now try to fill in the cell model. So if you try to fill this nucleons in the cell, then both proton and neutron will fill in the same state, that is 1p3 by 2. Okay, so for 1p3 by 2, the Jp value, that means the spin of a proton in that state equal to 3 by 2, and the neutron is also that same value. The angular momentum, orbital angular momentum value is equal to for proton is same and for neutron is same. Okay, so as it is a odd type of a nucleus, so what you have to find to find the spin of the nucleus? We have to apply the Northern rule. Okay, so try to apply. Now if this arrangement is odd according to the Northern rule, then the spin of the nucleus is Jp plus Jn. So put the value of Jp and Jn. These are same. Say 3 by 2 and 3 by 2, you will get a 3. And try to find the parity equal to minus 1 to the power Lp plus Ln. Okay, so Lp and Ln are both are 1. So minus 1 to the power 2 equal to a positive parity. Okay, that means the spin parity of the daughter nucleus is 3 to the power what? Positive. This is for lithium. Okay, for this. Okay, so what we are getting? We are getting that it is 0 positive is converting into 3 positive, and there is a spin of addition of a spin of outgoing particle. Okay, so now you see the positive sign here on the top of this 0 and 3. This positive means there is a even parity of the parent nucleus and the daughter nucleus. That means after the reaction and before the reaction, the parity is same. Parity is what? The parity is positive or even parity. That means what? That means there is no change in parity, as both daughter and the parent nucleus are holding the same parity, same sign of parity. That means what? That means there is no change. There is no change in parity between the parent nucleus and the daughter nucleus. So that's why del P equal to 0. You see, this del P equal to 0. So if del P equal to 0, then what is the value of L? That means the orbital angular momentum of the outgoing particle, electron or neutrino, antineutrino or positron and neutrino. What is the change? What is the angular momentum, orbital angular momentum taken by this outgoing particle? Definitely it should be 0. So L equal to maybe 0, maybe 2, maybe 4, maybe 6, like this, all even number possibles. Okay, but if you take L equal to 0, then you cannot get del J equal to 3, because J equal to spin of electron and antineutrino. This J is nothing but the change in this J is nothing but del J. You see, this equal to this. So if you want to find 3, then if you put L equal to 0, okay, and as S cannot be more than 1, because as you see, S equal to either 0 and 1. This is our restriction. You see, this L can be 0 or can be 1, and L cannot take more than one value. Okay, yes, it can take two values like 1 and 0, but it cannot take like this value 2 3 4 5. No, it cannot take. It can take only two values, that is 1 and 0. Okay, so if the value of s is can be 0 and can be 1. Okay, so if you take l equal to 0, so to get del j equal to 3, because j equal to, you know, j equal to l plus s. Okay, so if you take l equal to 0 and you have already know that j equal to 3, this j, this j, this j, and this j equal to del j, change in parity, change in spin. Okay, so j equal to 3 and you also have l equal to 0, so that means l should be what? L should be 3, but we cannot have s equal to more than 1, so the s value can be 0 and 1. So to get the value of a del j or a j of outgoing particle equal to 3, we should have L value is equal to 2. Okay, so 2, if we put L equal to 2 and S equal to 1, then only you can get the value of J equal to 3. Okay, and if you take this condition, this is nothing but the second order transition, and as S equal to 1, we know that if S equal to 0 it is Fermi, and if S equal to 1 it is gamma Teller, and as it is L equal to 2, that means it is second order forbidden gamma Teller transition. Okay, now you see, but in the question it is given that it is not allowed by pure gamma transition. Okay, this is not allowed by pure gamma transition, and it is and it is taking second order forbidden gamma Teller. So option C may be correct. Okay, option C may be correct. Okay, but we cannot say that this is the correct one. Okay, can be correct. Okay, so to confirm this, we have to solve, or we have to know whether this option D or D is correct or not. Okay, so let's see whether this whatever statement is given in the option D is correct or not. Okay, let's see. Remember that this is nitrogen is in fast structure state. Now you see whether it is correct or not. This is not option D. Okay, option D is starting from this. Okay, let you see. In option D, oxygen is converting into nitrogen and it is a beta positive decay. Beta positive means a proton is converting into neutron. Okay, that's why you see there was 8 number of proton, and it is in the right hand side you have 7 number of proton. Okay, now you see this oxygen 14 means even nucleus, even types of nucleus. That means the spin parity equal to 0 positive. Okay, and you see nitrogen in the fast accelerated state. Remember, nitrogen is in the fast accelerated state after the beta decay took place. Okay, you see now, and it is a order type nucleus. What? This nitrogen is a order type nucleus. So to find the spin period of this nucleus, we have to apply the Northern rule. Okay, and as it is in the fast accelerated state, let's suppose it is in the fast accelerated state, for simplicity. Okay, so the last proton or neutron will stay in 1d 5 by 2. Okay, it will not reside in this state 1p 3 by 2. Okay, as if it is mentioned that it is in the ground state, that means the last electron or proton will reside in this state. But as it is mentioned that it is in the accelerated state, and we are assuming that it is in the fast accelerated state, then the last proton and last neutron will reside in this state 1d 5 by 2. Okay, for 1d 5 by 2, okay, for 1d 5 by 2, the Zp value equal to 5 by 2, and spin angular momentum value equal to 2, because the d value L equal to 2. Okay, and p value L equal to 1, like this. Okay, and for both proton and neutron, same values are coming. Okay, so that's why apply the Northern rule. and this quantity is giving you 9, and it is an odd number. So if it is odd number, the spin of this nucleus, that means nitrogen, is 5. Okay, now find the parity. Parity equal to minus 1 to the power Lp plus Ln. So minus 1 to the power 2 plus 2. So it is even parity. That means what? That means we are getting that 0 positive is coming to, it is converting into 5 positive plus there is a spin of outgoing particle. Okay, and parity equal to what? Parity equal to 0, because this is even and this is even. Positive. Positive means what? Even parity. That means whatever parity was holded by the this parent nucleus, that much parity was present with the daughter nucleus. Okay, so change in parity equal to 0. Okay, so now if this del p equal to 0, and we cannot have if you put, let's suppose, okay, you see del p equal to 0, so the angular momentum taken by this outgoing particle, electron, neutrino, antineutrino, electron, neutrino, like this. So this pair will take L value, total angular momentum, sorry, the orbital angular momentum equal to 4. Okay, now you see, if you take L equal to 1, then there is a change in parity, because what, we know that parity depends on L value. Okay, so that's why we have to take only even numbers of even values of L value. That means L can be 0, can be 2, can be 4, can be 6, like this. You cannot take the value of L as odd values, because if you take the values as odd values, then the parity will be changed. That means this positive sign is no longer a positive sign here. Okay, that means it may be positive, that means it may be negative, this may be positive, or this may be negative, this may be positive, like this. Okay, so as we are getting both positive parity and the parity change equal to 0, that means what? That means the change in the orbital angular momentum taken by this outgoing particle is restricted to even number. It may be 0, it may be 2, it may be 4, it may be 6. But if this L value equal to 4, the S value is equal to 1, because S value cannot take the value more than 1. Okay, it is can be 0, it can be 0, it can be 1. Okay, so to find the value del j, that is the change in spin of the parent nucleus and the daughter nucleus 5, as I have seen, this del j, this is equal to del j, change parity of outgoing particle is equal to del j. So if you want to find the del j value equal to 5, then we have to take L equal to 4 and S equal to 1. Then only you can get L plus S as a 5. Okay, then only it is possible. Okay, so that means what? If this S equal to 1, that means it is gamma modular, and as L equal to 4, that means it means what? It is fourth order forbidden. So it is fourth order gamma modular transition. Then what kind of reaction it is? If it is not pure Fermi transition, it is fourth order transition. So option D was not correct. Okay, as it was fourth order gamma modular transition. So which option is correct? We have doubt on this option C. Okay, and we confirm that as this option D is also incorrect, so option C is the correct one, because it is given that it is not pure gamma modular transition, and we are getting what kind of reaction it was for option C. For option C, we are getting that this is a pure gamma modular transition. It is not sorry, it was, we are getting that it was second order gamma modular transition. That means what? It is not pure gamma modular. Second order means forbidden, means what? It is not pure gamma modular transition. Okay, so option C is the correct one. Hope you got all the answers. Okay.